So,
sorry, now the announcements are done. Please go ahead.
okay. Good morning, good afternoon, good evening, everybody.
Is YouTube
So
still?
welcome.
Oh, sorry.
No problem. So good morning, everybody. Good evening, afternoon, because depending on your time zone. So welcome to the 2021 IACR Distinguished Lecture. So I am Michel Abdallah, the current IACR President. As you may know, the IACR Distinguished Lectures, they have been awarded by the IACR since 1994, and they are usually they are awarded to people who have made important contributions to cryptology research. So the actual venue in which these lectures take place, they alternate between the general conferences, meaning they alternate between Aerocrypt, Crypto, and Asiacrypt. And this year, we have the pleasure to have this lecture at Asiacrypt. So it is an immense honor for me to introduce Andrew Yao, our 2021 IACR Distinguished Lecturer. So just a bit of information, although most of you are extremely familiar with Andrew. So Andrew obtained a PhD in physics from Harvard in 1972 and a PhD in computer science from the University of Illinois at Urbana-Champaign in 1975. So he's currently the Dean of the Institute for Interdisciplinary Information Sciences at Tsinghua University. But prior to that, Andrew also held professor positions at MIT, Stanford, UC Berkeley, and Princeton. So Andrew's research interests include algorithms, cryptography, quantum computer, auction theory, and artificial intelligence. And he has made many fundamental and outstanding contributions to all of these areas. And of course, because of that, Andrew has received many awards during his career. And here I would like just to mention three of them. So first, Andrew received the Knus Prize in 1996. He also is well known for having received the Turing Award in 2000, which is one of the most, if not the most prestigious award in computer science. And very recently, this year, he received the Kyoto Prize in advanced technology. So in addition to these awards, Andrew is also a fellow of the American Academy of Arts and Science, a fellow of the American Association for the Advancement of Science, a fellow of the ECM, a foreign member of the U.S. National Academy of Sciences, and a member of the Chinese Academy of Sciences. So in today's lecture, Andrew will be talking about probabilistic reasoning and cryptography and machine learning. So please join me in welcoming Andrew Yao. Please, Andrew.
Well, thank you very much, Michelle, for the nice introduction. I think that from now and then I saw on my screen that the network is unstable. So if somehow during this next hour, the connection is not quite great, I hope you would forgive me.
No problem.
It's really nice to be here.
It might help the network if you turn off your
lecture.
camera.
Can you hear me? Oh, turn off my camera?
Yeah, it might help the network.
Oh,
just
okay.
yeah.
Let me see, how do I'll stop video, yes. Okay. Well, great suggestion. Now I know why you are the chair.
except it didn't work.
And okay, as you can see
Yes,
that these two subjects look very different, cryptography and machine learning, but they are tied together by the being used often, and I'm very interested in this subject. And so today I'd like to talk about an open problem called the decay equality problem in cryptography, which has to do with the loss of privacy amount. And the other subject is about some mathematical aspect of the kernel method of machine learning. I'm going to discuss a very classical k-party, k-equality communication problem, which has been open for some time. And I will introduce the problem, and then I'm going to tie this k-party problem to a coding problem. And so I would analyze the protocols and introducing something called a distributed XOR code, and proving something about this XOR code, and using that this coding result. And to begin with, we are interested in this multi-party computation setting. K-parties want to compute a function with all their different n-bit private data. And they would like to compute this function using protocols. I'll go through a few rounds for protocols. What's the best protocol that approach this problem is called communication complexity, which was proposed in 1979 to address some aspect of these questions. And many areas, including cryptography. For example, the do some multi-party computation can also be regarded as what's the amount of inevitable privacy loss about the data that you have to leak if somebody is listening. That I will be focusing on is the k-equality problem. So we have k processors and then a referee. So that's the k+1. And there's a certain function g that and the processor pi would send a randomized string alpha I to the referee, and the processor, the referee, after collecting all the strings that have been submitted, then will use the function g in order to decide whether the exclusive OR of these k strings bit by bit is so that the function would be exactly the parity function of these n-bit strings. And the interesting case is that we are allowing randomized algorithm, and also we are allowing a certain error epsilon, and the communication cost is the maximum length of the string, or sometimes and the communication complexity is the minimum communication cost in terms of the number of bits of any such k-party algorithms. And we are focused on the simplest possible model, the simultaneous message model, in which only one round of communication takes place and then decide. And let's use the symbol complexity for the quality problem. And for k equal to 2, it's been known for a long time, almost 25 years, that there is a non-obvious solution that takes square root of n bits by the two parties. And also, it was the optimal complexity of the question. So there's a long list starting with the 96 and 97 Baba and Kimmel and Barnes paper, and there are many versions and variants, and also notably there's a relatively recent paper by Botshech, Gavetsky, and Clark in 2015 that gives a very ingenious, nice proof of the result. For k greater than 2, it's easy to see that one can generalize the known construction so that it will be, instead of n to the 1/2, you in general, it's a bigger power of n when k becomes larger. And however, the optimality question remains open since that early times, and there were partial results along the way, but the general question has been open for a long time. And in this talk, I would like to focus on this problem and show that actually this upper bound is also a lower bound. And so, as I mentioned, that the way that from the k-party problem, two parties, and think about it from the coding perspective, and because then that code will have some restrictions on the structure of the code, which is make it. And to begin with, let's discuss the concept of coding for a one party. It's a kind of standard type of code, but we're interested in randomized code. And so a code would be a collection of distributions, rho sub x, where x is any n-bit string. So this is a collection of distributions over a output string. So if the message you want to send is n-bit long, then this would be each of the rho x would be a distribution over the n-bit strings. So in other words, if I see a string input n-bit code to generate a probability, a random string. And we'll be focused on the particular case that the input x will be a uniform random input. And of course, in general, it could be some other distributions, but I think for the purpose of this talk, we'll focus on the case when a random variable x is a bit string, it's a uniform random input. And if I take t IIT samples according to the distribution then the receiver will learn about x more and more. So that means that the entropy of x from the point of view of the receiver would decreases more as more samples are. At what point would the the random variable would develop collisions in the sense that the entropy of X gets smaller, that something happens. And so the collision threshold of rho to be CT of rho, which is the minimal number of messages that the receiver has to receive before there will be significant collision taking place according to the samples. So more precisely, it's just the minimal t, so that if I take two random samples according to this distribution, mu t, what's the probability of getting a collision? And of course, there are many different thresholds one can develop and for different purposes. But here today, we'll just focus on this particular threshold. And now, so next, I would like to introduce some fairly high threshold. And this is going turn out to be the key to lower bounding the communication complexity of the K equality problem. I seem to have a little.
We can hear you.
I think my connection is a little bit unstable, so that I cannot.
I think it's okay. Like sometimes it cuts a bit, but I think most of all, I think it's
okay. Okay, thanks.
we are able to follow.
Okay, so I'll continue. Now, I'm going to construct a class of codes with the following description. Codes. I can construct something called XOR code based on this the randomized codes denoted by row tilde is this collection. And each one of them is a randomized code. And so in order to code a input string W for the code row delta, I would randomly decompose W into this exclusive or sum of K random strings. And so with the constraint that they add up to W. And secondly, I would generate a random string according to the row I based on Xi, and then output the collection of K random strings as the output of this XOR code. And we would refer to the lengths M1, M2, MA of the random strings as the shape of the XOR code. And so now the following theorem shows that the XOR code is quite resilient. And the theorem can alternatively be viewed as an extension of the XOR lemma. So what is said is this: if row tilde be any n-bit K XOR code with shape parameters M1 to MK, then theorem 1 says the collision threshold of this code has very high threshold. So if you can see that if M1 to MK, they are much less than N, then develop collision. So in other words, if someone leaks the information of the message for each eye, getting some information about about the information xi, then altogether they will reveal so little information about the original input W that you get very little information about it. And that is the essence that you can use it, the basic idea, to show that the kind of the leaked message kind of separately, then it will take a long time before you learn anything about it. And in a way, that's the main technical theorem. But then it takes a lot of effort to make it work. Okay. Yeah, I think you probably can still hear me, but I cannot.
Yeah, no, yes, we can hear you.
Okay, and now we're going to use it in order to show the complexity about the K equality communication complexity problem. And so the theorem 2 is to show that algorithms that you can have in terms of order of magnitude. And now the essence is that a protocol for the K equality problem can be interpreted as an algorithm for solving the 2 equality problem. So can reduce the K equality problem to a 2 equality problem, which, as we said, has been well studied, and we have a lot of insight about it. And the deduction is that the the first player is the original first player. So it's using M1 bits, and all the other K-1 other players are collectively controlled by a single player. And now, on the other hand, because of the nature of the K-party setup, that the player B is committed to using a K-1 XOR code with the shape determined by the individual players. The length of the bit that player sends has to be greater than the collision threshold of the K1 XOR code of the second player. So that's a result that the Botesh in the paper that I mentioned, they used that idea so and use theorem 1 to get the n to the K-1 divided by the product of the messages, and therefore now use the total number of messages sum no result. And yeah, I think that I'm still.
Yeah, this last part I could not hear much, but it's okay. I can hear you back now.
You're back now.
Yeah. Can you hear me or not?
Why divide it, why reduce it to two-party? And indeed, alternatively, it's possible to regard the K equality problem as a one-party problem, except this time it's not the K equality. So problem using the K XOR codes, and it's possible to use that approach to derive the bounds that we mentioned, except I think it's more natural to do it with the two-party case, because the zero testing, I think it just seems to be such a trivial problem. How can you get any lower bound? But I think that, okay, so this, that's the part about the my first topic I want to say. And the second topic I'd like to say is something about the machine learning algorithm. And I think it actually a very exciting trend. And because from the algorithmic point of view, it really emphasizes a different algorithmic paradigm. And it has wide applicability, but very little theoretical understanding. And so the research issue is that to explain the behavior of machine learning, whether it's good or why it doesn't work. And these are challenging problems for, to say it's a new algorithmic paradigm, because for many years that we tend to think about the design of algorithms is a logical process. Basically, we would take a problem and we would try to understand it to every possible mathematical structure knowledge, and then we would design an algorithm, and we know beforehand that the algorithm definitely would work, and quite often with explicit analysis of the performance guarantees. However, the machine learning plausible way to do things, and applied to things that might not have a really good reason for it to work, but it turns out a lot of times that they work well. And so it's a very interesting subject. Means it's a difficult problem where you try to explain something and to and that has no intrinsic logic that is transparent. And so I think from the theorist point of view, and so today what I would like to talk about is a example. I think it's perhaps one of the most familiar methods in machine learning, and it's the kernel method. And we would like to do an analysis for some problems. And so machine learnings are definitely being widely used in all domains, and the quality of solutions rely mostly on empirical evidence with little theoretical backing. And the current state of affairs is that really the applications run far ahead of the scientific understanding. Well-known problem, I just discussed a couple mentioned. The first one is about robustness and improving the stability of the machine learning. For example, here is the well-known example that if you have pattern object recognition, and here is a picture that's perfectly diagnosed, classified as a pig. But if you put randomness, and there are examples that it actually turns into some robust than the typical algorithms we do. And the second example is certainly, I think that people talking about a lot, explainable AI and the transparency of machine learning, namely that in order for the learning algorithms to be widely adopted, in many cases, people have to have confidence in it. So didn't put some bias into it. Now here is something that people often talk about. You have the appraisal of homes based on the data. So the machine learning designers take in a lot of the data in the neighborhood of the house and design a system, and from that time on can be used. And so, for example, if somebody put in a application and get a $2 million price tag, and so the person might get can I trust the result? And but the machine learning algorithms, a lot of times it's not possible at the present state of affairs to explain with the same mathematical rigor. So that's so this kind of question are very important, and I think that the analysis is the first is one of the first fix such problems. And so, but currently, the analysis of the machine learning algorithms is in a very kind of different days. So, okay, and so let's do it for a particular simple case, and that's something called the kernel method, and it's widely used in pattern analysis. And basically, the method uses something called a kernel function, which is a similarity function to predict whether a data point belongs to some cluster or not. So you can think of this kernel method is trying to do classification, making a prediction algorithm. And let's just look at an example of the simplest case, the linear kernel, and also the Gaussian kernel. And now, using the kernel method to do machine learning, it works well in many practical cases. And but there are also many exceptions. And one particular well-known hard case is the parity function. And the kernel method seems to have difficulty of getting very accurate prediction of this function, the parity, which is supposed to be really simple. And there have been plausible arguments suggested why the kernel methods don't work very well, but there's so far no really rigorous proof, and we would like to prove that the parity function for, in particular, the Gaussian kernel. And now to look into it a little bit, let me just go through the basic definition. The kernel function K is a similarity function from Rn, cross Rn to the set of real numbers satisfying the positive semi-definite conditions. And namely that the gram matrix K of Xi, Xj is positive semi-definite for any x1 to xm in the space. And the burning, so the kernel method is a kind of is a matrix of this form and satisfying certain conditions. And the learning a Boolean function with the kernel function K goes like follows. You first collecting data, and then you learn to predict kind of you get an algorithm from this data called a predictor. And finally, you can apply the predictor to make predictions. So the collecting data phase would take n random samples from the Boolean cube. So they are coded as 1 and -1 from a certain distribution. And now you do something to learn to build an optimal model for predicting F. And basically you do this, the class of predictors that you want to design is the simplest one. It's just a linear function. So it's satisfied by, so it's specified by the n+1 numbers in a linear function. And you want to optimize it in the following fashion. The first, it will fitting the data so that if you use these parameters, then you can get the same sign as the F. So basically, you would want that the kind of the particular linear function that you constructed here, that if you use this as a predictor, then it will at least fitting the data from where it came from. And secondly, among all the possible n+1 tuple of numbers that define the linear equation, you want to choose the one that have the maximizing margin. So you want it so that the prediction maximal of the linear functions. And once you get the prediction, you can use it. If you take input, Boolean input y, you would predict the value of fy to be the sign of the predictor. And so the error probability, the performance measure would be, in our case, let's just assume that all the numbers are randomly chosen over the Boolean cube. A proportion of the input for which that this predictor makes the wrong prediction. And as you can see that in the case of the linear kernels, the kernel function is just simply the inner product of the y's, and the predictor would correspond to a hyperplane that's separating the labeled sampled points into two groups, the true and separate the inputs and the maximization over the margin is simply to minimize the largest distance from both the red and the blue point to the separating plane. So the maximum, the margin means to minimize the max distance. And the second example, use this kind of Gaussian function as the similarity function. So it's try to emphasize points that are close together and give it more weight as compared to points that are dissimilar, And I think that sensibly this lambda would be choosing moderation. Otherwise, you would either try to too much emphasis on the points that are very close, or to equalize all the contributions, and so that you might not get a good information that you like to extract. And so using this, the predictor is given by a function that is linear in the kernels, but of course, it's a nonlinear function of this particular form. And Gaussian kernel is one of the most commonly used kernel method in producing classifier in many scenarios. And the question is that what's its implementation and why? And empirically, the Gaussian kernel method doesn't work well for the parity. And I think from the theoretician's point of view, at least we should understand this simplest phenomena. And if we can understand anything about me, we should be able to understand this particular case. And so we would like to confirm it analytically. And this problem has a big cannot compute parity, and Aspinaz in the 1990s showed that no small degree multivariate polynomial can approximate parity well. So linear polynomials or quadratic polynomials and so on wouldn't do as a predictor. But of course, the Gaussian is not a polynomial. It's a infinitely many terms. And now Bengio observed very early on that there's a good reason why, at least a plausible reason, why the Gaussians don't learn the parity function well. So with very large lambda, the parity function can be expressed with a n+1 Gaussian. So that's a that's an argument for that the Gaussian kernel might have a chance, but immediately they also suggested that the Gaussian kernels will not learn well because the linear combination is not of the form of the standard learning. It can come up from a very smart theoretician who look at it and say that we can design a linear combination of n+1 Gaussians that can solve problem exactly. But however, if you want to do some real learning, kind of using the methodology that I just mentioned and try to learn from the data, then actually Bengio et al. They think argument. And so very recently, we showed that the Gaussian kernel cannot learn parity for various ranges of lambda. Here, we will just prove it for the case when lambda is in the most reasonable, sensible choice, 1 over the square root of n. And the statement will look like this. For this parameter, if with very high probability, a random Gaussian parity predictor P that is chosen according to the methodology we mentioned, it will have error rate involving very heavy probabilistic conditioning and reasoning. And so I think the central to the proof is to set up a high level view that reduces the problem to simpler pieces. Each one of them requires solving a non-trivial stochastic processes. Okay, yeah, and so let me give me a little bit outline. Random sample points, and we use it to produce a Gaussian parity predictor. This is a linear function, and it's useful to regard this predictor as a hashing function that would hashes the different sample points into the real space. And so what we would like to do is that would produce a predictor, which from the point of view of the hashing functions that do too well a good job, so that independent of whether they are parity is +1 or -1, they would just hashes them together in a sort of evenly distributed way. And so essentially this research of designing, kind of analyzing universal families and so on of hash functions. So why is it that this randomly choose function from this particular hash function would be a very good hash function? That is the problem. And so let me give you the several steps for doing it. First, let's kind of prove the result under the assumption that that these coefficients AI, they are exactly equal to +1 or -1 according to the parity for all i's. And later we'll relax this assumption. And so what we'd like to do is to construct a probabilistic argument to show, take a random sample, we'll get a predictor that's a very effective hash function. And so this function cannot well separate points without even parity, and leading us to conclude that it makes a very high error. And the difficult part is that if you compare the randomness, the big is in the random set, so it is true that it's specific 2 points, then a randomly choose hash function would hash them to different locations. But the point is that you would like to argue now that so it's easy to get the probabilistic statement from one side, but actually what we want to see is the other end of the point. And these, nonetheless, there are standard type laws in order to do probabilistic reasoning to transfer this type of results. And so the central argument will start with proving this. So let me just show you the results. So if you take points which are fairly distant apart, then they would, it's very hard to get a bad random is bigger than epsilon for a random y prime in A, and the lemma shows this. And so that's exactly the intuition that I gave. And now, after we have done that, let's remove the restriction that AI say +1 or -1 according to the parity. And so by consider the maximum margin condition for the parameters, and one use optimization theory, it's possible to infer that the AI is equal to the parity of xi plus exponentially small terms. All the derivations in the previous proof, and therefore does not affect the conclusion. And so to summarize, a rigorous analysis of machine learning algorithm behavior can invoke quite subtle probabilistic reasoning, and such understanding will help us build a firmer foundation for machine learning. So in conclusion, both cryptography and machine learning are rich cross-disciplinary areas that need foundational research. And foundations that laid during the 1980s for these areas in cryptography and deep learning have led to amazing applications nowadays in digital economy and the AlphaFold today. And I think that probabilistic reasoning key to resolving many of the problems of a stochastic nature that arise in these settings. And two examples were presented in this talk today. Thank you very much for coming to the talk.
So thank you, Andy. So now we have time for a few questions. So if you would like to ask questions, you can actually feel free to unmute yourself. So, and yeah. So
I actually have a question.
Yes.
go ahead,
Uh,
Kevin.
It's partly my misunderstanding. It may be due to the audio breakup, but could you explain again the role that the kernel you used plays in the analysis in the middle of your talk? You referred to two examples of different kernels.
I'm only analyze the Gaussian kernel because the linear kernel is well known that it cannot learn the parity function well. I think that actually any fixed degree or small degree, even fraction of n, it is known by Aspiness in one of the references that I mentioned. They show that they cannot distinguish the parity more than 50% of the time. And is that it has high degree.
So this is specific to the problem of learning parity then?
That's right. That, I think that in general, really do not know how to analyze it. I think the parity it's the simplest kind. I think that one thing I want to say is that what's different about the analyzing machine learning algorithms is that proof that something does not work. That we don't have any good experience with it because I think that in the old days that algorithms ask the question that, can you show me that why it doesn't work? However, this is a question that makes sense in the machine learning context because the hope is that you would design general purpose machine learning situation. So therefore, we would like to understand why it works and why it doesn't work. I think this is it's kind of tied up to the things in the when people analyze dynamic systems. And if I give you a dynamic systems and I ask the question, can you show me that it doesn't behave or does it converge? And you will have difficulty doing it. I mean, except for the well-known cases. And I believe this is a very interesting subject for probabilistic reasoning. Is that I think that it makes sense for us to try to develop a technology for proving things that don't work.
Okay, maybe I should explain why I was asking the question. In machine learning, a lot of the goal is to model human perception, to be able to generalize human inferences. And so, for example, in image processing, we try to find similar images. But there's this ancient result from the 1970s by Amos Tversky about how human perception of similarity is not properly represented by a metric space. And so the kernels you were using are actually embedded in a metric space. And I wonder how much of the difficulty of machine learning predictions is due to the fact that they're using this faulty measure of similarity. It's a complicated question, and I've asked several machine learning experts this, and they sort of, you know, as mathematicians, we prefer using simple measures, and you know, that's why we're always referring to the Gaussian distance instead of other metrics. But you know, similarity is not actually a metric. There's this wonderful paper. I'll send you an email about it.
Yeah, please do. I think that's a very interesting point. I think that I think it will be extremely intriguing to be able to design that are alternative to the current metric space approach. And yeah, please send me the point to any reference, because I'm dying to hear some successful examples. I think that it would be wonderful.
I put a link to the paper in the chat, but
Here?
in the chat, but I'll send it by email.
Yeah, yeah.
Okay.
Okay, well, I can download it from here.
So
Okay, yeah.
does anybody else would like to ask additional questions?
Yeah, thanks for the
right.
paper. I think that that Tversky certainly is a big name.
Yeah, it's a very, very interesting paper, which I discovered, I don't know, 15 years ago.
Yeah, I think I got it.
All right. So would like to take this opportunity to thank Andy again for his talk. So it was very nice of you to be able to accept this invitation to give a distinguished lecture. And so if you have further questions to ask Andrew, you can always submit via the chat. We can always make sure to forward the questions to him. And so please, let's thank Andy again for his talk. Thank you, Andy.
Well, thank you very much, Michelle and Kevin and you. And I think, and thanks to all those that are present. I enjoy.
Yeah.
Bye-bye.
All right, bye.
Bye-bye. So I'll just leave. Bye-bye.